equilibria is taking place in physical means, then we should say that, right, phase transformation is taking place. Rate of freezing of solid is equal to the rate of freezing of liquid. Then it is considered as solid-liquid equilibria. In chemical equilibria, rate of forward reactions will be equal to rate of backward reactions. Hello everyone, I am Venu Prasad, Department of Chemistry, Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. Today I am going to take Unit 7, Equilibrium. It's session 1. So let us study what all there in the equilibrium. Why do we say that it's a term is considered as equilibrium? Let us study today. Okay. First thing is, now let us see the contents. Which and all is, now let us see first definition of equilibrium, types of reactions in the equilibrium, and classifications of equilibria, and equilibrium involving dissolution of solids or gases in liquid. Next thing is chemical reactions of equilibria, characteristics of equilibrium, types of chemical equilibrium, and laws of equilibria. Finally is equilibrium constant expression. Okay, now let us study the definition of equilibria. What do you mean by the equilibria? Equilibria means is when forces from both the sides, become equal, then it is considered as equilibria. According to the chemistry, it is a point. It's a point where chemical reaction, when rate of forward reaction becomes equal to the rate of backward reaction. In a chemical reaction, rate of forward reaction becomes equal to the rate of backward reactions. For example, conversion of water to ice. At what temperature water becomes ice? At particular temperature only we'll say that, right? It is converting from water to ice, means at particular temperature. Then in that temperature only their conversion takes place. That is known as equilibrium state, because it has been changed its phase from one form to another form. Then it is considered as equilibria. Okay. Next thing is types of reactions in equilibria. There are two types of reactions in equilibria. Which and all? That is, first thing is reversible reaction. Another one is irreversible reaction. What do you mean by reversible reaction? A reaction in which occurs both in forward and backward direction is called reversible reaction. Means conversion of water to ice, at ice to water, that is known as reversible. We'll get, right, if the reactant is converted into product, after some time we need a reactant. So what we have to do? Conversion of product to the reactant. Then it is considered as reversible reaction. Example is conversion of water to ice or ice to water. So we'll get same thing, right? So that is considered as reversible reaction. But if we are going for irreversible reaction, a reaction in which only takes place in forward direction, but not in backward direction, then it is considered as irreversible reaction. Reaction which takes place only in forward direction. Conversion of water from liquid state to gaseous state. From gaseous state will we get a water? No, right? So then it is considered as irreversible reaction. Example is conversion of water to vapor state, then it is considered as irreversible reaction. Here reaction from product will not get a reactant, so only from reactant to products conversion takes place. Okay, then it is considered as irreversible reaction. Next thing is classification of equilibria. In equilibria there are different types of classification. There are two types. First thing is physical equilibria, second thing is chemical equilibria. What do you mean by physical equilibria? Physical equilibria means, here it is a equilibrium. It is always a equilibrium in which two opposing forces that takes place simultaneously. Then what will happen? Physical change takes place. If two simultaneous forces takes place simultaneously, then there will be change in physical change. So then it is considered as physical equilibria. It is a physical equilibria. Example is water and water vapor in the equilibrium in a closed container. closed container. What will happen? Water from liquid state to gaseous state, it has been converted, but it is in a closed container. So what will happen? That is called as physical equilibrium. Why? Because if you keep a water in closed container, what will happen? Here, just you will take a water and you will just heat it in a closed container. So when the water is in the liquid form, it gets converted into gaseous form, but gaseous form it will be converted, but there will be no abstraction of gases from to outside to the environment, because we have kept this reaction in closed container. But there is a physical change, right? Because before you applying a internal energy to the closed container, water is in the liquid state. But after, if you are supplying internal energy to the closed container, what will happen? Just from liquid form to gaseous form, it has been converted, but it has been not reacted with atmospheric temperature. So only physical change has been takes place. There is no chemical change. If there is a chemical change, if you are saying, means what we have to think? We have to take water in a open container, then we have to supply a internal energy. When you supply a internal energy, what will happen? Water gets converted into vapor state and it is reacted with atmospheric temperature. When it is reacted with atmospheric temperature, then all the gases which is present in atmosphere will be reacted. So there is both physical and chemical changes also takes place. But here in physical equilibrium means you have to do the reaction only in terms of closed reactions, closed term, because there is no chemical change, only physical change you have to observe. So this is considered as physical equilibrium. At particular temperature, water which is in the liquid form gets converted into vapor state. So you can see the some amount of vapors in the closed container. So we can say that, right, this much amount of temperature is required for this type of water to convert from liquid state to vapor state. Okay. Next thing is, equilibria is a physical process. What do you mean by physical process? Most common equilibria involving both physical process are of phase transition. Always equilibrium takes place, correct, but it involves physical process and which is a phase transition takes place. If equilibria is taking place in physical means, then we should say that, right, phase transformation is taking place, phase transitions, but not others. Okay. First thing is solid liquid equilibria. What do you mean by solid liquid equilibria? It is a equilibrium in which rate of melting of solid substance, is equal to the rate of freezing of liquid. Means if you have taken one solid, then it is converted into liquid state. At particular temperature, it is converted into liquid state. Okay. After some time, for example, today I have taken ice. At particular room temperature, it is converted into water. Correct, right? 0 to 25 degrees Celsius. Okay. At 25 degrees Celsius, it has been converted into water. Same, now it is in the 25 degrees Celsius. Correct, right? That is in the liquid state. Now it has been it should require to convert into ice form. So what we have to do? We need some amount of temperature. What we have to say that, right? Just from 25 degrees Celsius to 0 degree, you have to bring the temperature. Then only water gets converted to ice form. That is the phase transition. Okay. Here it is a equilibrium in which rate of melting of solid is equal to the rate of freezing of the liquid. Then it is called as solid liquid equilibria. Okay. Example is, in a closed system at 0 degrees Celsius, ice and water attains the equilibrium. At 0 degrees Celsius, ice and water attains the equilibrium. At that point, rate of melting of ice is equal to rate of freezing of water. So H2O is converted into, see there, solid form and this is a liquid form. Here, rate of freezing of solid is equal to the rate of freezing of liquid. Then it is considered as solid liquid equilibria. Okay. Next thing is liquid vapor equilibrium. What do you mean by liquid vapor equilibrium? It is a equilibrium in which rate of vaporization vaporization is equal to the condensation. Rate of vaporization is equal to the condensation. Then it is considered as liquid vapor equilibrium. Example is H2O is converted from liquid state to gaseous state. Okay. Here we should know that, right? Liquid vapor equilibrium means rate of vaporization is equal to the condensation of vapor. Means what we can understand here? Here, if you keep a water in an open environment at 25 degrees Celsius, it gets evaporated, you will come to know. Or 30 degrees Celsius, it will be evaporated. Just we can think that. Okay. Now, if we keep a water in a laboratory, then if we take a water in a laboratory, let us take one water and keep it in a laboratory, supply little amount of heat. Then we have to maintain a temperature for 30 degrees Celsius. Then we have to observe that whether water gets converted from liquid state to vapor state. We should see. So we can say that, right, here they have said rate of vaporization is equal to the condensation of vapor. Means here it takes place naturally in the environment. We should know at what temperature water is evaporated in the environment. We should know that. Next, in your laboratory, if you have taken today water in a beaker, then if you supply little amount of internal energy, we should know that at what temperature it gets evaporated. Then only we can say that rate of vaporization is equal to the rate of condensation of vapor. Means here in your environment around 35 degrees Celsius, water gets started evaporating. Let us think. Then if you are doing that same experiment and same water in the laboratory at 35 degrees Celsius, your water should get evaporated. Then only we can say that rate of vaporization is equal to the rate of condensation of vapor. Okay. Then it is considered as liquid vapor equilibria. Now let us see that solid vapor equilibria. What do you mean by solid vapor equilibria? In solid vapor equilibria, rate of vaporization of the solid is equal to the condensation of vapor of the solid. Means today if you have taken one solid, now let us think one solid. For example, I2, iodine. Iodine in the solid state is equal to the iodine in the vapor state, they have said. Now let us take iodine balls. Okay. Now let us expose iodine balls to in the open environment. Okay. At what temperature it will be converted into liquid form or gaseous form, we should see. Then we have to note down that temperature. Then now let us take that iodine balls. Then what we have to do? We have to use this, or we have to see at what temperature, right? So we can take that iodine balls in the laboratory. Then we can see at what temperature it will be vaporized. Then both temperature you should match. Means for example, in environment all types of gases will be there. So temperature will be around 25 to 26 degree, let us take. But in the laboratory, we should think that around 20 degrees Celsius it will be converted, because it is a closed system there, only atmospheric temperature. But in the open state, if you are doing that experiment, means all type of gases will be present in the atmosphere. So we should say that iodine's temperature, explosion of iodine takes place only from 22 to 27 degrees Celsius in the range. So we should think that always we have to preserve the iodine below room temperature. Then only it can be perfect. Otherwise, we cannot preserve the iodine. You can see now, for example, in the medical shops and all, we can see hydrogen peroxide. Always it has been kept in the refrigerator. If you keep it in the open environment, what will happen? Just it will be converted into water. So hydrogen peroxide means H2O2. Always it is kept in the medical shops in below 5 degrees Celsius, because it should not be exposed to the open environment. Like that only iodine, if you open and keep, if you open the lid of the iodine bottle and keep in the open atmosphere of the laboratory, what will happen? You can see some amount of gases, and we can see the iodine balls has been converted into whitish form. So we should not keep the iodine in open bottles, just we have to preserve it. Okay. Next thing is solid solution equilibrium. What do you mean by solid solution equilibria? Now let us see, when a slight excess of solid solute, now slight excess of solid solute is added to the fixed amount of liquid solvent, then what will happen? Some amount of solid solute remains undissolved. It remains undissolved. It appears as dissolution process. That has been stopped. But actually, both dissolution and crystallization takes place simultaneously. Then it is considered as solid solution equilibria. For example, sugar solute plus solution they have said. Now let us take sugar in a solution phase they have said. Means we have to take one sugar solution, okay, which is dissolved in water. Now let us take one water and little amount of sugar has been added. It has been dissolved. After some time, now let us add little amount of sugar to that. What will happen? After a particular time, it gets undissolved. So I have said it amount of solid solute remains undissolved. Correct, right? If you have taken a sugar solution, for that after some time, if you add little amount of sugar to that, what will happen? We can see around 5 to 10 minutes, it gets undissolved. After 10 minutes, it gets dissolved. Correct, right? So first I have said it is undissolved. Then it appears as dissolution process has been stopped, because for 10 to 15 minutes, it will be like that only. Slowly it starts to dissolve. Correct, right? So we can say that dissolution process has been stopped. Both, but actually dissolution and crystallization takes place simultaneously. Both crystallization and dissolution takes place simultaneously after some time. So we can say that it is a solid solution equilibria. So at particular temperature it should come, right? Then only it starts to dissolve. So that is considered as solid solution equilibria. That is considered as sugar in the solid state is equal to the sugar in the solution phase. Okay. Now let us see gas in gas solution equilibria. What do you mean by gas solution equilibria? It's an equilibrium in which rate at which molecules of the gas go into the solution phase, Molecules of the gas goes into the solution phase, that is equal to rate at which molecules of the gas in the solution phase, goes back to the gas phase. Means just we have to take one container which contains little amount of solution. Then what will happen? When you dissolve a solid substance or some amount of chemicals in a water, some amount of gas will be liberated. That gas has been gone to which place? Solution phase. Correct, right? Why? Because when you dissolve a chemical in a water, it is dissolving. When it starts to dissolve, some amount of gas will be liberated. Then when gas liberated, we should think that that solid has been dissolved. So we can say that molecules of the gas goes into the solution phase. Then that is equal to the rate at which molecules of the gas of the solution phase goes back to the gas phase, they have said. Means just we have to think that first we have to take one container which contains water. For that little amount of chemicals has been added. When you add a chemical, when it starts to dissolve, some amount of gas has been liberated. Then we have to think that first thing is, when gas has been liberated means we should think that that chemical has been reacted with water. Then they have said that solutions which is gas which is present in the solution has been converted into gas phase, they have said. Why? When it will be converted? Just when you supply little amount of internal energy. When you supply little amount of internal energy, gas which is present in the solution gets converted into gaseous phase. It will be reacted with atmospheric temperature. Correct, right? So then it is considered as gas solution equilibria. Okay. Next thing is reversible reaction, and second thing is irreversible reaction. If you are going for reversible reaction, it's a reaction in which reactant to form product. reactant reacts to form products under certain condition, at particular condition, and products also react to form reactant. Then it is considered as reversible reaction. Means, for example, can we say some conversion of water to ice to water. At particular condition only, it gets converted into ice, and ice gets converted into water at particular condition. Then it is considered as reversible reaction. Okay. Next thing is irreversible reaction. What do you mean by irreversible reaction? It's a reaction in which only reactant combine to form products. Reactants combine to form products, but products cannot be converted into reactant form. Means just reactant has been converted into product, but not from product to reactant is not possible. So then it is considered as irreversible reaction. Okay. Now let us see the graph of reversible and irreversible reaction and how the equilibrium state has been reached. Let us see. Okay. Here you see, if hydrogen reacts with iodide, we will get hydrogen iodide. Okay. And it is a equilibrium state actually. Okay. Now this is a forward reaction. Okay. Then if you are going for reversible reaction, reverse reaction, from reverse reaction means backward, back. Okay. From products to reactants. So that is considered as reversible reactions, we can say. So 2Hi has been converted into water molecule and hydrogen molecule and iodide we got. At particular condition, they obtain a equilibrium state. So we should know that at particular time and particular reaction rate, then only this reaction takes place, and you will get some equilibria. Means, for example, we should say that at particular time only this reaction takes place reversible. At particular time, at particular condition, then only reversible reaction takes place, but not at simply we cannot do the reversible reaction. So I have given that a chemical equilibria is such a state at which reversible reaction, in which velocity of forward reaction is equal to the velocity of backward reaction, such that concentration of reactant and product do not change. Concentration of product as well as reactant do not change with respect to time. If you have taken 10 ml of water which you convert into ice form, then again if you are converting ice to water, same 10 ml only will be there. There will be no decrease in concentration, there is no decrease in the volume what you have taken. Then only we can say that it is a equilibrium state. Okay. Next thing is characteristics of chemical equilibria. First thing is, in chemical equilibria, rate of forward reactions will be equal to rate of backward reactions. Next thing is, position of equilibria is not affected by the catalyst. There is no affection in the catalyst. Second thing is, at equilibria, concentration do not change, because in equilibrium means we should know that it is a reversible reaction. There is no change in concentration, there is no change in volume. Then only equilibrium can be said. If there is change in volume and all, we can't say that it is a equilibria, because reactants what you have taken, it has been converted into products. After some time, product has been converted into reactant. Then only that is considered as reversible reaction. Then only we can say that equilibrium state can be attained, we can say. But we cannot say that, we can't say if there is a change in concentration, then it is considered as equilibrium. Okay. Next thing is position of equilibrium. Position of chemical equilibrium can distribute by varying the pressure, temperature and concentration. By we can say that some stage we can change the concentration, pressure and temperature. Next thing is, it is independent of initial concentration of the reactants and product, but it depends upon the temperature. It is independent of concentration of the reactants and products, but it is dependent on temperature, because we can't change the temperature. If you are changing the temperature, what will happen? We can't say that it is a reversible reaction. Correct, right? So these are the some characteristics of chemical equilibria. Next thing is types of chemical equilibria. There are different types. First thing is homogeneous chemical equilibria. Second thing is heterogeneous. Now let us see what do you mean by homogeneous equilibria. It is equilibrium is said to be homogeneous. It is said to be homogeneous if reactants and products are in the same phase. Both should be in the same phase. Then it is considered as homogeneous equilibria. Example is hydrogen, which is in the gaseous state, and iodine also, which is present in the gaseous state. You will get a hydrogen iodide. Then it is considered as homogeneous. Means both the reactants should be in the same phase. Then it is considered as homogeneous. Okay. Here you see nitrogen and hydrogen. You will get ammonia. So then it is considered as homogeneous equilibria. Next thing is nitrogen oxalate. So you will get nitrogen dioxide. Now let us see methyl acetate. Methyl acetate is which is in the aqueous form. Water will be is also in the aqueous form. You will get acetic acid and alcohol. Heterogeneous equilibria. Heterogeneous equilibria means both the reactants. Heterogeneous means reactants and products are in the different phase. If you have taken two reactants or if you have taken only one reactant and you will get the products. But reactants and products are in the different phase. For example, now you have taken calcium carbonate. If you have taken calcium carbonate, always calcium carbonate will be in the solid form. When you keep it in the open environment, what will happen? You will get calcium oxide and carbon dioxide. But you have got a product calcium oxide, but another one is carbon dioxide, that is in the gaseous phase. We can say that both the products and reactants will be in the different phase. Okay. Next thing is, now let us take ammonium hydrogen sulfide. Okay. If you have kept in the open environment, what will happen? It is in the solid state. But if you keep it in the open environment, you will get ammonia in the gaseous phase as well as hydrogen sulfide will be in the gaseous phase. Why? Here you see you will get the products in the gaseous phase, but reactants will be in the solid phase. Okay. Next thing is NH2CO, NH4 they have taken. Here it is in the solid state, but products, here you see products are in the gaseous phase. So reactants and products will be in the different phase in heterogeneous equilibria. Next thing is laws of mass action, means laws of equilibrium. That is a very much important, means just how equilibrium takes place. They have set some law, which is means rate of the reaction is directly proportional to the product of active masses of the reactants. Product of active mass of the reactants at constant temperature. Then it is considered as laws of equilibria. Just they have said rate of the reaction is directly proportional to product of active masses of the reactants at constant temperature. Then it is considered as law of equilibria. Now it is a very important topic. They derive equilibrium constant. They have said expression. Okay, it is represented by Kc. Now let us take one reversible reaction. A and B be the reactants. You will get the product C and D. Okay. It is conducted in a closed vessel. You have taken this reaction and it is considered as reversible reaction. So what we have to say? We have to say that reversible reaction and it is conducted in closed vessel at constant temperature. Let concentration of A, B, C and D be the molar concentration. Here, so we have represented by square bracket. So it is represented by square bracket. Always we represent concentration in square bracket. Okay. Molar concentration of the reactants and products of which one all? A, B, C, D respectively. Let RF and RB be the velocity of forward and backward reaction. Now let us apply law of mass action. When you apply law of mass action, RF is directly proportional to concentration of A and concentration of B. Then if you remove the directly proportional and we can substitute one equilibrium constant. RF is equal to Kf. Kf means equilibrium constant of forward reaction into concentration of A and concentration of B. Where K is the velocity constant of forward reaction. Okay. Next thing is applying the law of action for backward reaction. How we can represent RB? RB means reaction at backward reaction, reversible reaction at backward state. Okay. RB is directly proportional to concentration of C and concentration of D. Correct, right? Now backward reaction means from product to reactants. Now let us remove the proportionality constant. So proportionality, if you remove the proportionality, what you will get? RB is equal to Kb into concentration of C and concentration of D, where Kb is the velocity of backward reaction. Okay, at equilibrium. Now let us take the reaction is at equilibria. So RF will be equal to RB. So Kf for reaction at forward or reaction at forward reaction and reaction at backward state. So we can write it is equal. At equilibrium, both forward and backward reactions will be equal. So I have represented like this. Okay. So now we have to calculate the equilibrium constant, right? Always equilibrium constant is Kc I have set. Here Kf will be equal to Kb. So Kc is equal to Kf divided by Kb. Then concentration of products divided by concentration of the reactants. This is the expression for equilibrium constant. In next session, I will be studying about the expression of equilibrium constant for the gaseous, reversible, homogeneous reaction. Gaseous, reversible, homogeneous reaction. This is about this session. Thank you.